Hi there. So I thought I'd make a video for this to show maybe a slightly more ordered way of solving these bridge kind of problems. Lots of you were getting the idea with this and getting right answers, and I think most of you are definitely on the path of doing it correct. But it doesn't hurt to kind of take a little bit more time and try. I'll try to do a little bit more neat for you. So what we do is this whole thing we're doing here is called the method of joints, and what it relates to is we're solving the forces on each of these members by um, looking at each joint separately. I think one of the better things to do would actually be to number these joints or letter them. I'll call that A, B, C, D, E, F, G, H, and I. And then I call this the force from this support or whatever. We'll call that a reaction force, call that RA. And there's one over here too, and call this RI. And I think what one I'll do is this. I'll do this one. So there's 1,000 newtons acting at point C, at joint C. First thing I'd like to do is find out what the size of these RA and RI are. We can use that just using our statics with equilibrium forces and torque. Just redrawing maybe what this would look like is if we treat the bridge as like just some beam sitting on these two supports, we have 1,000 newtons here, RA and RI. I could call this some distance x. Therefore, this would be some distance 4x. You see, like if each one of these little sections is x, you can see the distance from there to there is 4x. So torque around point A is equal to 0, the total torque. So 0 equals, say, 1,000 x minus RI 4x. So you get 1,000 x equals RI 4 RI, the x's cancel out. And you get RI equals to 250 newtons. And since RI plus RA is equal to 1,000, so all the up equals all the down, we know RA equals 750 newtons. Okay, so we know all the external forces acting on the bridge. Now we can start analyzing these members. So I'll start with joint A, and I'll redraw the joint here. So that's what the joint looks like. It has two members. There's this force, which is FAB. That's a good way to name it. And then the force going along here would be FAC. That's why it's nice to number or letter each joint. It gives us a good way to label each force. And then there was this RA. All right. You can see I've drawn both these forces as they've drawn both of these forces are showing tension. They're showing that this force is pulling on a joint and this is pulling on the joint. They're both showing tension. But we'll see what happens when we do some calculations here. So first I'm going to analyze the total forces on A vertically. So Y, total round of vertical forces is equal to 0. And this is 60 degrees. So I have FAB sine 60 degrees plus RA equals 0. So FAB equals negative RA over sine 60. So that's negative 750 over sine 60. And I believe that gets me FAB is equal to negative 866 newtons. So what's the significance of this negative sign? It means that I've drawn this as a tension member, but in fact, it's negative, so it's actually a compression. So if we go back up to our drawing of the bridge here, the force acting along here then is in compression. So I'd say the forces acting on it could look like that, compression. Alrighty. Then the total forces acting in the horizontal direction on A also have to be equal to 0. So as I've drawn it here, I have FAB cos 60 plus FAC is equal to 0. So FAC is equal to negative FAB cos 60, which is equal to, well, negative of a negative cos 60. 750 sine 60, divide that, and it was cos 60. Okay, 4033. All right. And that's a positive number, so in fact, FAC is in tension, just as I've drawn it. So we can come back up to my bridge here. That's members in tension. Okay. And we can continue on from there. So the next one we could do would be joint B. So I'll draw joint B. So this is FBA. It's joint FBC, and this would be joint F, or force, sorry, joint, force FBD. Draw that like this. We'll start with summing the forces in the y direction. Joint B. So we know that FBA sine 60 degrees plus FBC sine 60 degrees is equal to 0. Those signs, they cancel out. We know they're the same. So we get FBC is equal to negative FBA. And that we know is 866. It's like a negative of a negative, right? So FBC actually is in tension. We know that for sure. Okay, well, let's now find the forces in the horizontal direction. So we have sum of forces at B x equals 0. So FBD plus FBC cos 60, that's equal and opposite to FBA cos 60. So FBD is equal to FBA cos 60 minus FBC cos 60. So FBA, where was ours? That was negative 866. And then BC was positive. So they're both negative, so they're going to add together. So I got 866 cos 60. Half that's 400. That's twice that. So that's 866. Yeah, there you go. Twice that. So we get negative 866 newtons. So that's a compression. That's FBD. So it's this guy there. That's probably actually the weakest point on the bridge. I think that's going to be the highest compression. Well, actually, both those were right. 866. Those would be the highest compression forces on this bridge. And compression materials like wood or whatever, they'll break or fail in compression before they will in tension. This one we don't know. Well, we do actually. Let's do. Do we do that? FBC is in tension. BC is in tension. Yeah. So that is in tension. So we could do joint C now. It's probably the most complicated joint to analyze just because it has 4 members plus a force. So let's do that. So first I'll just kind of sketch out the joint. So that's FCB. This is FCA. I believe that's FCD, I think. And FCE. Let's just double check. Yeah, D. Okay. I'll do the vertical first. So the sum of forces at CY is equal to 0. So FCB sine 60. Oh, actually, and I forgot. I got the reaction. This 1,000 newtons down here. Okay. FCB sine 60 plus FCD sine 60 is equal to 1,000 newtons. So all the forces acting up are equal and opposite to all the forces acting down. And this is the one force we don't know. So we could say FCD sine 60 equals 1,000 minus FCB sine 60. FCB was 866 was a positive number. So I know this is 1,000 minus 866 sine 60. 866 sine 60 is that's the 750 newtons. So this is actually equal to 250 newtons. So FCD is equal to 250 newtons divided by sine 60. Uh, 60 sine 288 newtons. And that is positive number, so that is a tension. FCB is a tension. And I think that makes sense. You're pulling down on this joint that causes both those to go into tension. And at this point, we could actually just, as a double check as we go along, we should already be able to figure out the direction of all these diagonal members. At joint D, if this is pointing up, this one has to be pointing down to keep it balanced. Likewise, if this is pointing up, this one has to be going down. So it's tension. So they're alternating tension and compression. So that's compression. That's tension. Oops. That's compression. That's tension. And this compression. And that sort of makes sense because I would expect the end to be in compression as well. And these are all symmetrical, or symmetrical or the same. If this is 288 or 250 down, then that has to be 250 up. So it should always be 250, and it should match what this is. So let's just double check. If we think that is true, then if FHI vertical sine 60 should be equal and opposite to this, which was 250 newtons. And sure enough, if you go 288 sine 60, you get 250. Right? 288 sine 60. There you go. So we actually don't really need to calculate any of these beams. Again, they're all the same. They are all 288. The horizontal beams, though, those will need to be calculated each time, I think, or at least a few more times to figure out which each what the values of each particular one. Like I don't know, or maybe I do because if I had experience, but I don't know offhand if that's compression or tension, or it's not immediately obvious, I should say, because at this point, this one's moving the right, that's moving the right, this is moving to the left. Is this going right or left? That's the question. So let's do that one. We're going to figure out what FCE is. So sum of the forces at C in the x direction it's all 0. So FCE plus FCD cos 60 is equal to FCB cos 60 plus FCA. FCE is equal to FCB cos. So we know that CB, where is CB actually? FCB is 866 positive. Cos 60 is actually a half, so that might help us later. FCA. Where did I do FCA? I must have done. Oh yeah, there you go. 433. And then I'm going to subtract this one, FCB. 866. Oh, I have that written twice. What the heck am I doing here? Well, that's a D. It's 288. So 866 cos 60, it's a half, plus 433. Oops. Oh my gosh. 866.5, 433, add it, and then half of that would be 144. So we get 722. And it's a positive number, so it's in tension. So FCE is in tension. All right. Let's find out what this joint is by analyzing, or this member is by analyzing joint FD, or joint D. Just make sure I have all my, that's E and F. Make sure I have that right. Oop, no, I did it the other way around. E. That's F and E. Okay, so we know the size of those. We just have to, well, we have to be very careful of the of the positive and minuses. So FDC is 288, so it's positive. So FDE is negative 288. All right. And so we'll sum the forces horizontally. So we get FDF equals FDB equals 60. Nope, sorry. FDB plus FDC cos 60 minus the horizontal component of that, FDE cos 60. So FDB we found out up here was 866 negative. FDC was 288. Half of that will be 144 minus FDE minus negative 144. So that's negative 866 plus 288. Negative 578. So that FDF is negative, so it should be a compression force. So it'll be like that. All right. Let's do joint E. So I'll draw my diagram here first, I guess. Oh no, that's T. Let's see. This was, I think that's, what is it, G? That's F, and then G at the bottom. Okay, so that's the sketch of that joint. We knew once again, we know the diagonal member, so FED was a negative, and therefore FEF we know is positive. So that means it's in tension. I can always come back up my drawing and check that that kind of matches what I'm thinking. And yes, I've shown it in tension. All right, so sum of forces of E in the x direction are equal to 0. So FEG equals FEC plus FED cos 60 minus FEF cos 60. So FEC was 272, positive number. Oh, sorry, 722. FED was negative, so, and I've done this enough to know that's 144, so that's negative 144 newtons. And this is minus EF. That's also going to be a minus, like that. Because this is adding a negative number, and this is just subtracting a positive. Okay, so that's 722, 288 minus 434. And that's a positive number as well, so that's also in tension. So we got a lot of tension members here. We can analyze joint F. So this is force FD. This is force FE. And what do we got here? H is across and G is down. Like that. Okay. Sweet. FFE was positive 288 newtons. So FFG is negative 288. And once again, horizontally, FFH is equal to FD plus FFE cos 60 minus FFG cos 60. So FFD was negative 578. FFE is a positive number, so it's plus 144. And this is subtracting a negative number, which is 144. So we got 578, 288. Oops. Subtract that, get negative 290. And that is in compression. Interesting. So those top ones are in compression, the bottom ones are in tension. So I'm going to guess this last one's going to be in tension. And hopefully it's 144, because we already know this is supposed to be 288. Sine of 60 of 288 is 144. And that's what this thing should be. Let's just cross our fingers. So we're going to analyze joint G. G. So this is FGI, FGH, FGF, and that was FGE. All right. FGF was a negative 288. So FGH is positive 288. Horizontally again. So FGI equals FGE plus FGF cos 60 minus FGH cos 60. All right. Here comes showtime. FGE. What's FGE? Is that it? Where's my FGE? Oh no. 434. Okay. Plus, if GH is a negative, it's negative 144 minus 144. All right. So you got 288 minus. So good. So it's 146. That's because I'm rounding numbers off. We get. It's positive, right? Thank you. It's positive because we're expecting it to be in tension. Sweet. So we can see that the left component, the left horizontal component of that one balances the right horizontal component of that one. Done. So I mean, it's a bit of work, right? But just by doing these little drawings for each joint, being really careful of your positives and negatives, carrying these numbers across properly, you can just go step by step and solve any bridge. Actually, I shouldn't. Sorry, you can solve a bridge like this that has a solution. Not all bridges will have solutions.